Hi all, this is Mr. Yeager, looking at some skills you'll need to use for AP Physics. Obviously, throughout some of the introductory materials you probably saw, there's certain things that you should just be able, that you need to be fairly competent with to be able to succeed in this course. This is probably a particular skill that you have not done much of, and so this is what I want to introduce now, and you'll see that we will be using this throughout the course. When we are looking at trying to graph certain equations, try to calculate certain aspects of the different equations throughout the year in terms of it will work with every equation. Okay, so this is a single skill that can be used whenever there's an equation involved to create what's called a linearization or a linearized graph. Obviously, the other skills that you need to obviously be competent with is just basic algebra, one variable algebra. Okay, that's what we're looking for. And then your SOHCAHTOA, your trig. You have to be able to use very, very basic trig, be able to look at triangles and figure out maybe what's the side equal to if you have an angle in another side. But those you should already know coming in. Linearization is one you probably have not seen before. So I'm going to try to go step by step through this and also try to show you a couple examples of linearization. You might not get it right away, but it's something that you got to start thinking about. And if you really are struggling not understanding where it's going with it, you got to start asking questions immediately. A lot of free response questions do involve you linearizing a graph, finding something graphically. And usually that means that you have to use this process. Okay? So, again, the purpose of this is when we look at graphs, you're going to see, obviously, we're going to have curves a lot of times. All right, they're going to be exponential because a lot of the formulas that we use in this class have exponentials involved with them. Okay, we have that v squared. We have a lot of times v squared, t squared, omega squared, x squared. What do all these mean? Obviously, it's some value, but we have to be able to graph them. Again, if we make any graph that is x squared versus y, we're going to create some sort of curve, whether it curves up or curves kind of up and then flattens out. If there's an exponential involved, you know that creates a curve. We want to try to avoid that. This happens sometimes we don't avoid it, but we can't create any good information out of that in terms of calculating the exact number. So we want to linearize it. So that's what we're saying. Many formulas have this x squared component, which results in a parabola or a curve if you create a y versus x graph. All right. So the thing is that we're running into, okay, is again, here's examples of different formulas. Okay. We are interested in finding the variable in front of the squared variable. A lot of times the questions will say, graphically find a, which is called the acceleration. Okay. Graphically find a if you have data for x and t, not t squared, but t. Graphically solve for a. All right. Same question goes for this next formula, the elastic potential energy is 1/2 kx squared. If I give you the elastic potential energy and I give you x, I want you to solve for k. Graphically, how do you do that? So all of these are done the exact same way, just with different values, okay? And so this is your example here. Find the acceleration on position time graph, all right? The thing is, the problem, 1/2 a is the slope in the first formula above, but if you plot x versus t, you're going to get a curve. Same goes with the other formulas, okay? So we want to create, like, 1/2 a would be the slope, but if I'm looking at a curve, the slope is constantly changing, okay? It's constant. That's the whole idea of a curve, is you don't have a consistent slope, all right? So we decide that we linearize this graph. We change the curve into a straight slope line without finding new data or anything like that. We maybe just simply adjust the data, okay? And so this is how we do it without trying to use a graphing calculator, okay? You will have to be able to do this on graph paper, and you're going to have to be able to obviously scale it appropriately. We have to understand how to obviously follow through with this, okay? So the best way to do this is jump right into a problem. Okay, and so there's a problem that is on, that you can find on It's Learning, okay, or that we've done in class, and basically you use the following steps to complete the problem. So that problem is, let me get to that, okay, We're looking at this Joker problem. Yep. The Joker is hiding high up in a building, watching as the Batman hops into the Batmobile and zooms away. The Joker wants to determine the acceleration of the Batmobile so he can be prepared to escape from future crime in his own vehicle. He uses his Veneer phone app and collects the following data based on his video. Okay? So you can see, based on his video, the Joker's video, he's calculating the distance that the Batmobile moves away. Obviously not going that far away, only 281 meters. But he's measuring this over time. Okay? So we have distance and time involved with this particular problem. Okay? And you're going to see me kind of go back and forth with this quite a bit to try to go through the whole problem. Okay? Don't worry about the lab thing next week. All right? So, how do I linearize? Confirm you need to linearize. The question is asking you to find the acceleration of the Batmobile. All right? When it asks you to graph something, you use the data that's given to you. All right? You create a distance versus time graph of the data. Don't connect the dots. Okay? We're going to confirm that you get a curve. So let's go ahead and show this real quick. Okay? All right. Sorry. Going back one. Okay. So, let me go. I'm going to. This is exactly the same way I go through it in class. All right. We're going to go back and forth quite a bit. Okay. So, I'm going to go ahead and graph this distance versus time. I'm going to graph this distance versus time. Now, I kind of jumped one step. Why would I do distance versus time to find the acceleration? What you will eventually go to is you need to find a formula in your AP Physics formulas that has distance and time in it and has acceleration. The formula you go to is this one. Again, obviously you don't know what this formula is yet. Right now I'd have to give it to you. Later on you'd be able to figure this out. So this is the formula that has distance, which is going to be delta x, and t, which is time. Okay? So again, don't worry where I got the formula. You're going to realize these formulas are going to be taught obviously throughout the year. But your process is, this is the data I've collected. What formula has delta x and t in it, and it has a in it? That's so I can solve for it. All right? It's this one right here. And so the thing is, you might also immediately go, well, wait a minute, what the heck is v naught? That's the initial velocity. The initial velocity of this Batmobile is 0. So guess what? This can go out of your formula. So you're left with this. Delta x equals 1/2 at squared. Okay? 1/2 at squared. And so, based on this formula, if I want to try to make a line, I want to match it up with the y equals mx formula. And so if you line it up, you can see delta x should go on the y-axis, t should go on the x-axis. It's on the other side. Don't worry about the 1/2 a yet. Okay, we'll obviously explain how that becomes the slope. So, if I go ahead and graph this data, this is probably going to take me a couple minutes just because I'm going to actually go through each data point. All right, just like you would. All right, so you have 0, 0. Let me get a different color. 0, 0, followed by 0.5 and 0.81. So based on my graph, I mean, it's going to start off very, very, very low. So I'm going to put it like way down here. Okay, just above 0.5. Okay, oh. All right. 1.2, 4.7. 1.2, 4.7. Okay, still very, 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 very low because again, you can see my first axis is 50. All right, 1.2 and 4.7. Okay, you'll see how this forms after some time. The beginning is actually very, very important that you kind of do this and take your time with it. Okay, 1.8, 10.5. 1.8, 10.5. Okay, so now I'm finally raising up a little bit. Okay. Next one. All right. 2.1, 14.3. 2.1, 14.3. Still not that much higher. Okay, it's not going to be perfect, obviously. All right, and you're not going to make it perfectly. Take your time, though, to it. 2.6, 22. 2.6 and 22. I probably put those up a little bit higher than they should. All right, 22, finally about halfway through. Probably should be over a little bit, but that's okay. All right, 3.7, 44.5. 3.7, 44.5, so almost up to the 50 mark. 3.7, probably again, I'm kind of a little bit left on everything. I'm actually going to go back and do that one again. Okay. 5.5 and 98.3. 5.5, 98.3. 5.5, 98.3. So vroom, zooms up pretty quickly here. Okay, almost done. 7.1 and 164. 7.1 and 164. And then finally, 9.3 and 281. 9.3 and 281. All right. So if you look at this, does this look like a straight line? Okay, we don't want to just connect the dots, but I mean, we should be able to see that we have obviously this curved shape. Okay, we have an exponential graph. All right. I didn't talk about it for scaling. I hope basically you're all good at scaling. What I do is I look at what's the lowest and what's the highest number that I need, and then obviously scale it in between accordingly. Obviously, if I have kind of a weird number, like the last one's 281, I'm not going to scale it to 281. I'll go just above that at something I can break up. I feel like you should always break things up in terms of 1, 5, 10s, 15s, 20s, and so forth. You should, I mean, you can use whatever you want, but it doesn't need to be ridiculous. It shouldn't take you a long time doing it. All right, so you can see I create this particular graph. All right, so let's go on back. All right. So we have a curve, which means, and we'll learn this as well when we talk about distance time graphs, if you see a curve on it, that means that you are accelerating. Okay? So what would be next? Okay? What would happen next? All right? We got to change the axes to make a linear graph. Okay? So your first graph is done and simply confirm that you're accelerating, but what can you change the axes to so that a straight line could be made? Now you can see I have my answer, distance versus time squared. Distance versus time squared. How do I know I need to change the time to time squared? All right. And this is the part that people struggle with most. This is the part that I regularly have to go over and over and over again. What we are doing is this is the official linear line equation. Y equals mx plus b. This is the line equation. If your equation follows this, and you graph something y versus x, and it follows this graph, this equation exactly, you should get a straight sloped line, a linear line. What we are doing, and you saw me do the initial step, is I line up my formula that I'm interested in using underneath of that. So again, y equals mx plus b. I'm going to put delta x underneath of it. 1/2 a t squared. Now there's no plus, so there is no y-intercept. Okay, the y-intercept should be 0 for this, and that makes sense. The cars will start at rest at 0 time and should not be moving yet. Okay, and if it starts at rest, obviously, actually, technically, we could have more, and we'll see that in a little bit. Okay, but 1/2 a t squared. What we're saying is we just graphed delta x versus t, and we got a curve. That's because if I do delta x versus t, because t is squared in the formula, I'm getting y versus x squared. Okay? I'm getting a y versus x squared graph, which causes me to get a curve. So what I do instead is I incorporate that square into my initial data. What I'm going to do is I'm going to graph delta x versus t squared. Delta x versus t squared. I know what the delta x's are. I know what the t's are. I can then manipulate either one, whatever I want to do with it, to basically figure out how to appropriately graph it at that point. So this is where people get confused because they're like, I didn't measure t squared. I measured t. Well, then what are you going to do with all the t's then? Square them. If you have t, square it, and now you have t squared. And so that's what we do. Okay, that's what we go back to. If I go back to my problem, basically what I do is I create a new column and I make them all time squared. How do I do that? I just square all of them. 0 squared is 0. 0.5 squared is 0.25. 1.44, 3.24, 4.41, 6.76, 13.69, 23.04, 30.25, 50.41, and 86.49. Okay, so what did I do? I squared each of the times. Why did I do that? Because according to my equation, to make it a perfect line equation, I have to graph delta x versus t squared. Not t, but versus t squared. And if I do that, whatever is left will become my slope. I should get a straight line. So again, because I have the data, because I know what the distance is and I have the times with those distances, you can then manipulate whatever you want with those two sets of data to appropriately graph that line, okay? And so that's what we're going to basically do, okay? So you can see I'm not going to do anything to distance. That's why I have this second graph. It's going to be distance versus time squared. I want to use the exact same distances. All right, the exact same distances, but now I want to use the times, okay, time squared. All right, so here we go. So you can see I don't change anything about my y-axis, but my x-axis obviously is a whole lot larger now. Instead of 1 through 10, it's 9 through 90. Again, I try to break it up into something that's nice and simple, put it by tenths, basically. So 9, 18, 27, 36, and so forth. All right, so again, a lot of the data is going to be really close initially. So 0 and 0, I don't know why I even looked at that one. 0, 0. Next one, 0.25, 0.81. Okay, so like this is going to be barely off the ground at all. Okay, basically already still on the line. Okay, and again, this is very common. You're going to see I'm going to have a ton of data points right stuck at the beginning there, but that is extremely important to do to get this actually very accurate. When we do labs in the classroom, those initial data points at the very close parts of it are very important, and then usually I tell you to spread out from there. 1.44, 4.7. Okay, 1.44, 4.7. So again, not much higher. It's basically a big clump down there. Okay, next 3.24 and 10.5. 3.24. Still very, very little change. Okay, very little change. 4.41, 14.3. 4.41, so basically halfway, 14.3. Okay. 6.76 and 22. 6.76 and 22, so about 2/3 apart and about halfway up now, between 0 and 50. All right. 13.69 and 44.5. 13.69, so I finally passed 9. And 44 point, is that what it was? I think it's in 44. So a little bit below it. A little bit below. Nope. 23.04 and 74.9. 23.04, so close over here, and 74, basically right in the middle. Okay. 30 and 98.3. 30 and 98.3. 30 and 98.3. 50.4 and 164. 50 and 164. Oh, get in my own way. I know this is really exciting. Stick with me though, it's going to work out. Okay. And 86.49 and 281. 86.4 and 281. All right. Look at this. All right. That is definitely not a curve. Okay. And I know we kind of like the thing is we shouldn't be expecting a curve. Okay. We should be looking at a straight slope line now. So what is my next step? Okay. And I'll probably go back through the PowerPoint at it one more time. My next step is to go ahead and create a best fit line through these. All right. It might not go through all of them perfectly, but the whole idea would be, how can I try to line all these up exactly? I do a best fit line. Okay. I could see it basically doing something like that. Okay? And you know, part of it is my own plotting, but essentially these are going up in a fairly straight line. And so now that I have this straight slope line, I can go back and solve for the official problem. Okay, so let's actually go back to the PowerPoint because I probably skipped a couple steps there. Okay, if I go back to the PowerPoint, we changed it. Okay, oh, skipped a step. Okay, so we actually have done a lot of steps here all of a sudden. Okay, so we changed the axes to distance versus time squared, which means I change all my times to time squared, but my distances don't change. Nowhere in the formula or anywhere else did it say to change their distance. You create a new graph, x versus t squared. You rescale the t squared axis, and then you create your best fit line. Now, I've changed from this. I used to say draw two best fit lines. Okay, and again, this won't be perfect. The dots won't line up perfectly. If they do, you probably fix the data. Okay, and you don't want to do that. You want to try to let your data fall where it is. Okay, now it says one best fit line won't be enough. I'm going to go and tell you I did switch that. This is from a couple years ago. One best fit line is good enough. So you just draw through one best fit line. Don't worry about saying need two. One is good. Okay. So the rest of this, where it says 2, 1. Okay. So find the slope of your one best fit line. Okay. Your one best fit line. All right. So the thing is here. I see this mistake all the time. Okay. Is when I find the slope of my best fit line, I need to pick two completely new data points that are on the best fit line. Just because the data point happens to fall, that one of your blue data points, one of my blue data points falls on the line, does not mean it is actually physically in their line, okay? It might seem like that, but you need to pick two brand new data points. So what I would do is, obviously make it simple on yourself. Pick an axis and go across, and hopefully it falls on a nice point. But on graph paper, use a particular vertex. Okay, find where you can clearly make a distinction between the two. On mine, you can't. All right, so I'm going to say 250. All right, and maybe 71. So this data point is 71 and 250, and then my other data point, let's go from 100. All right, is 26. So 26 and 100. Obviously, if you have to estimate a little bit, that's okay. They are expecting you to have a little bit of error involved. But now we can go ahead and solve this. 250 minus 100 over 71 minus 26. This is 150 over, what's that? 45? 45. And 150 divided by 45. I have found my slope. My slope to be 3.3 meters per second squared. How do I know it's meters per second squared? Distance in meters over time squared. This is my slope. Okay? My slope. Now the thing is, you are actually not done. You've got to be very, 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 very careful. You have found the slope, but there's a very important final step. You might be done, but it depends on the formula. Okay? It depends on the formula. All right? Go ahead and then, obviously in this we're calculating the acceleration. The thing is, your equation is this 1/2 at squared. The x is the y, t squared is the x. Everything else is the slope. So your slope is 1/2 a. Your slope is only equal to 1/2 the a. So this right here, this 3.3, is equal to 1/2 the acceleration. So what's the actual acceleration? Multiply by 2, 6.6 meters per second squared. That the slope is whatever is left in the formula. You might have to divide or multiply something out that they give you in the problem. But in this one, it's 1/2 a. It equals acceleration. Now, I want to be very clear with this. What I then get immediately some students to think is, every single time you find slope, it's 1/2 a. It is for this equation, for this problem. Not for every problem. It depends on the formula you are using. I can't stress that enough. I have a lot of people that when they finish this, they're like, I don't really get it. Does it always equal 1/2 A? No, 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 no. Okay? It depends on the problem itself. It depends on the equation the problem's asking you to use. Okay? So, again, you should now have, well, again, we're ignoring the high and low slopes. Ignore all this. We don't really do error analysis anymore. So common mistakes is people don't change the axes. They sit there and go, I don't know what to do. What do I do with it? I just don't get it. It's like, guys, what equation are you going to use? What are you trying to solve for? What data do you have? What equation has all of those things in it? Okay, according to the equation, do you need to then square either the y or the x-axis? Okay. Obviously, step number 2 is they go, yeah, I found the slope. This is my answer. But is it? Is the slope exactly equal to the acceleration? Is it exactly equal to what you're solving for? Make sure you recognize maybe it's only equal to half of what you're solving for. Maybe you have to multiply a mass out. Okay, I'm going to go and tell you there's all different things you might have to do. Okay, and then obviously you need to do best fit line. And people always use their old data set, and they sit there and go, "Why am I so much farther off?" You're using your old data set. You pick 2 new points, make it easy on yourself. Don't pick decimals and stuff. Make it nice and simple. All right, and solve. Okay. So again, based on that PowerPoint, no 2 best fit lines. 1 best fit line is enough. All right, and we can solve. I'm going to do one more problem to kind of show you how to go through it, and we'll go from there. Thanks.